Section 6.3 is applications of normal distributions. In 6.2, recall that we did the standard normal distributions, where the mean is 0 and the standard deviation is 1. Now we're going to be looking at normal distributions where the mean is not 0 and the standard deviation is not 1. So on our calculators, when we had the standard normal distribution, I said you could go to the normal CDF to find probabilities. You use your left bound, right bound, all that good stuff. That's all you had to put in was your left bound and your right bound. Now we're going to be adding to that the mean and the standard deviation. So what we'll be looking at on our calculator is the normal CDF. We'll still use our left bound and our right bound separated by commas, but now we're also going to add in there our mean and our standard deviation for the distribution. That's what's going to be different in this section. Now, this author teaches you how to find probabilities using normal distributions by converting everything to a z-score and using the table that comes with the book. Not everybody got the book, so I'm going to be teaching you how to do this using this feature of the calculator. And do you remember how we got to this on our calculator? Second, bars, and then you just look for the normal CDF. I think it was number 3 on my calculator. And some of the newer operating systems actually prompt you to put in the left bound, the right bound, mean, and standard deviation. It doesn't. But do you remember this formula? We went over some of this on the first exam. I gave you this formula for converting data values to z-scores. The z-score is simply the number of standard deviations either above or below average. When we looked at the standard normal distribution, we referred to the z-scores. If a distribution or a data value is above average, we have a positive z-score. If it's below average, we have a negative z-score, and the average value is your mean. Now, we can convert any normal distribution to a standard normal distribution by using this z-score formula. The shape of the distribution is going to be the same. The shape right here is going to be the same. It's just that the numbers along the x-axis, instead of having a mean of mu, we're going to have a mean of 0. Instead of this being a data value of x, it's going to be a z-score. But the shape and the probabilities and everything are exactly the same. We just use the z-scores to convert our normal distribution to a standard normal distribution. We're going to get around that by using the calculator, but here is the procedure for finding areas with a non-standard normal distribution. First and always, I said you want to sketch a normal curve. Always draw a picture. It makes it easier to find the probabilities. Sketch a normal curve, label the mean and any specific x values, then shade the region that represents the desired probability. This is the probability you want to find. Are you looking for the probability that x is less than a number or greater than a number? Do you shade to the left? Do you shade to the right? That's what I'm talking about here. For each relevant x value that is a boundary for the shaded region, we can convert that number to an equivalent z-score and then look that up on a table. But what we're going to do is we're going to bypass these two steps and we're going to use our calculator to find the probabilities. That's using that normal CDF feature. Let's look at an example problem. Tall Clubs International says Tall Clubs International has a requirement that women must be at least 70 inches tall. Given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, find the percentage of women who satisfy that height requirement. So what we're looking at for women's heights, we have a normal distribution. The mean is 63.8 and the standard deviation is 2.6. That information will be given. You have to know the mean and the standard deviation. So our first step then would be to draw a picture. What number do we put in the middle here? The mean is 63.8. And if we go out one standard deviation above, we have to add what number to the 63.8? 2.6. Now the shape of this distribution is the same as the shape for our standard normal distribution. It does have the mean of 0. The Tall Clubs International requires that in order to be a member, you have to have a height that's at least 70 inches tall. Here's the 70 out here, 70 or more. At least means we want 70 or more. So it's going to be a very small percentage of the population of females that qualify for this Tall Clubs International. So what are we going to do to find this probability of this shaded region? That's what we want to find. We go to normal CDF on our calculator, and what are the numbers that we plug in? Left bound first. We read left to right, so we put in our bounds left to right. Right bound, a really big number. 100 might get us there, but just to be safe, we're going to go for 1,000. Because this graph goes off to infinity right here. It's going off to infinity, so I just need a really big number. What number am I going to put for my mean of my distribution? 63.8, there's the mean, and then the standard deviation is 2.6. So we go to our calculators. We hit second bars, we find normal CDF. Oops, it was number 2 on my calculator. The numbers we plug in are 70, comma, really big number, comma, 63.8, comma, and 2.6. So here's what we end up getting. That means then that this is the probability of a woman being 5'10" or taller. If we change that to a percent, that means that only 0.8% of the female population should qualify. Do you see how this is very similar to what we did in 6.2? Alright, finding values from known areas. Don't confuse z-scores and areas. Z-scores are distances along a horizontal scale. Areas right here is the probability. The z-score is the distance along the x-axis. Z-scores are distances along a horizontal scale, but the areas are regions under the normal curve. This is true. A z-score must be negative whenever it's located to the left half of a normal distribution. Since the z-score corresponds to the standard normal distribution, where the mean is 0 and the standard deviation is 1, doesn't it make sense that if you have a z-score to the left here, that this would have to be a negative number? And then we would have our positive z-scores to the right of 0. Z is along the x-axis, though. The shaded region under the curve corresponds to the probability. Procedure for finding values from known areas or probabilities. If we know the probability, then what do we use on our calculator to find a z-score? The inverse norm. And that's right under the normal CDF on your calculator. You're still going to start by sketching a picture. Draw a picture of a normal distribution, enter the given probability or percentage in the appropriate region of the graph, and then identify the x values that are being sought. How we do this is by using the formula from the z-score. What they did right here to get this formula was they solved the z-score formula for x. If you have z equals x minus the mean divided by the standard deviation, all they did was they solved this equation for x. There's no need to memorize another formula unless you just want to. Actually, I'll let you write down your formulas. You can have a formula sheet for this test. This is what we're going to use then once we figure out what the z-score is. Here's a sample problem, aircraft cabins. It says when designing aircraft cabins, what ceiling height will allow 95% of men to stand without bumping their heads? Men's height are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. So here the men's heights are normally distributed with the mean of 69.5 and a standard deviation of 2.4. And what we want to do is find this height here that allows at least 95% of the men to stand without hitting their head. We're looking for the x value. Now we know this z-score because we've gone to our calculator in 6.2 and we did the inverse norm on this, but we'll go ahead and do it again just so you can see what it looks like. We clear the screen out, we hit second bars, and then inverse norm is number 3 right here. We plug in 0.95 because we want the z-score that separates the bottom 95% of the population from the top 5%. And when we do that, we get 1.645, which is the z-score that I've circled right down here. If I use the formula for z-scores, the formula being z equals x minus the mean divided by the standard deviation, and I plug in the numbers that I have, z I have 1.645 equals x minus, what am I going to plug in for the mean? Divided by, we just set up a linear equation that we can solve. So what we're going to do is we're going to multiply both sides of this equation by 2.4. What you do to one side, you got to do to the other. That way you've maintained equality. This 2.4 will cancel out here. And what's 2.4 times 1.645? 0.95. How about that? So when we do that, we end up with x equals what? Why don't we call that 73.5? Just rounding to one decimal place. And the units here are inches because we were given our height measured in inches. Now, if you didn't want to solve this equation by memorizing this formula, we could have just plugged in the numbers into this formula, which is already the z-score solved for x. So when you're working with applications with a normal distribution, the first thing you've got to ask yourself is, what is it that you want to find? Do you want to find a probability or do you want to find a value of x? If you want to find a probability, that's where you're going to use the normal CDF. And we're going to put in our left bound, right bound, the mean, and then the standard deviation. If you want to find a value from a known probability, that's where you use the inverse norm. Alpha is what I'm calling this shaded region right here. And there's a reason I'm calling it alpha, and you'll find out as we get deeper into the course. So once you decide what you're going to find, that determines which feature of the calculator you're going to use. We're going to be using the technology. We don't have to convert things to the z-score because on our calculators, we can type in the mean and the standard deviation for the problem that's given. Here's a problem to practice now. It says men's heights are normally distributed with a mean of 70 inches and a standard deviation of 2.8 inches. Let me write that down. Men's heights are normally distributed with a mean of 70 inches and a standard deviation of 2.8. I know that's different from the previous problem, but you got to play the cards you're dealt. For this problem, this is what they're saying. Women's heights are normally distributed with a mean of 63.7 inches and a standard deviation of 2.5 inches. The standard doorway height is 80 inches. Part A of this question says what percentage of men are too tall to fit through the standard doorway without bending, and what percentage of women are too tall to fit through a standard doorway without bending. So for part A, what we want to find is, if we draw a picture of a normal distribution for the men, what number am I going to put in the middle? 70. And I want to know what percentage of men are taller than what? 80. 80 is going to be somewhere out here. I don't know where, but it's going to be out there. I'm looking for that percent. For the women, draw a picture of a normal distribution because I was told that their heights were normally distributed. Draw them a curve. What number goes in the middle for the mean? 63.7. And how tall is the standard doorway? And that's going to be way out here, isn't it? So how do I find the area of that shaded region? By the way, that area of the shaded region represents the percentage that are too tall to fit through the standard doorway without ducking. How would I do that using my calculator? Normal CDF. What is my left bound? Right bound? Mean? Standard deviation. For the women, everything's the same except for the mean and the standard deviation, isn't it? So now we go to our calculator. Second, distribution, normal CDF. We'll do the men first. We have a left bound of 80, a right bound of a really big number, the mean of 70, a standard deviation of 2.8. And there we go. For the women, I'm going to hit second enter. Everything stays the same except for the mean and the standard deviation. So I'm just going to type over our mean and standard deviation. For the mean, we've got 63.7, comma, 2.5. What this means is, do you see the e to the negative 4? That means that this is scientific notation, and there's a decimal that's moved 4 places, 1, 2, 3, 4, to the left from this number. So this represents the number 0.00018. Well, look at this one down here, e to the negative 11. That's 0.000000035. The question was, how come it's not 11 zeros? Why is it only 10? Because one of the decimal places out of the 11 that we use is to move the decimal from behind the first digit. Oops, I made a mistake. I was talking and writing, so that's 3, 6, 7, 8, 9, 10. Okay, that makes more sense? Alright, good. What this means is there is a less than 1% chance here and here of having somebody, actually this is less than 0.1%. If I'm rounding, I got to say 2. Less than a 0.02% chance of having a man too tall to walk to have to duck to walk through a door. Here, this is just very, very, very small. We're going to say less than 0.0001. Typically, that's what we do is 0.0001. I'll do the same thing over here. And here we'll say less than 0.0001. That was part A. Part B says if a statistician designs a house so that all of the doorways have heights that are sufficient for all men except for the tallest 5%, what doorway height would be used? Well, this is a different question now. We're going to build a custom home, and we just want to make the door tall enough for the shortest 95% of men to fit through. If a statistician designs a house so that all of the doorways have heights that are sufficient for all men except the tallest 5%, what doorway height would be used? Well, let's draw a picture of what it is, the information that we're given and what we're asked to find. We start with a normal distribution because men's heights are normally distributed. And what we want to know is what should this height be right here that separates the bottom 95% of the population from the top 5%. Now remember, men's heights are normally distributed with a mean of 70 and a standard deviation of 2.8. And I'm going to try something with your calculators because I think what we can do here to save all of that algebra that y'all were so fond of is do inverse norm 0.95, comma 70, comma 2.8. I bet it gives us the x value that we're looking for. What do you know it does? Great. So you don't even have to do algebra. This number right here represents the bottom 95% of this shaded region right here. The 70 is the mean and the 2.8 is the standard deviation. So now it's color coded for you. X is the 74.6. X is 74.6 inches. So if I was rounding, I'd say that doorway needs to be 75 inches tall. Who wants to measure 0.6 of an inch? But now 95% of the male population can walk through your door without having to duck. So if you're looking for a probability, we use the normal CDF. If you're looking for an X value, we use the inverse norm. If you take that probability and separate or put behind it the mean and the standard deviation, it solves you from having to use the z-score formula and algebra. It just gives you this value for X right here.